As people talk about quantum computing, certain industries come to mind. So financial services, and they tend to come to mind almost always with new technologies. And because any win they get, given their ROI, let's say, if they get one, is going to be very good and they can capitalize very quickly. We hear a lot about chemistry, although we have to be very careful because people are still talking about things like hydrogen, and others are aspiring to folding proteins, right, and things like this. But today we're going to talk about energy, and particularly the energy industry. Along the way, should you want to make any comments about the amount of energy actually used by these systems, or Paul, indeed, because there are other quantum technologies like sensing, like timekeeping, we'll make this a little bit broader, talk about quantum technologies as they relate to it. So, as I said, let me make sure I have the right set of questions for you all. Okay, so first, I could have remembered this part. Who are you? We'll go down. So who are you? Who do you represent, and why are you here? That is, what is your role here to speak about the energy industry and quantum?
So, hello everybody. Tim Rogers. I'm with IonQ. I'm a quantum solutions engineer. So I'm more focused on the go-to-market side. I have the extreme liberty to look at all sorts of applications across all sorts of different verticals and industries. But I happen to come from the power industry. I was in the nuclear power space for a number of years. And so I'm particularly passionate there, and particularly passionate about how our systems might be able to help reduce some of the power consumption of some of the future workloads in the compute space.
Tim?
I'm Jeremy Renshaw, Executive Director for AI and Quantum at the Electric Power Research Institute, or EPRI. If you've never heard of EPRI, that's okay. It means you don't work in the energy industry. It's kind of one of those binary. If you know EPRI, you work in energy. If you don't, then you don't. But EPRI is a global nonprofit focused on safe, affordable, and reliable energy for the human race. And if you look at the levelized or inflation-adjusted cost of energy over the last 50 years since EPRI has been in existence, it's actually gone down over time. So I would see that as a success for not only the utilities around the world that we work with, but also EPRI as well. So that's what we do.
And I'm Paul Lipman. I'm with Infleqtion, where I'm Chief Strategy Officer, but really do everything but the kitchen sink at the company. And we've been involved in quantum computing, quantum sensing, quantum timing, for quite some number of years, have done quite a bit of work in the energy sector, and looking forward to the discussion here.
So I'd like to start with really just almost a roll call of application areas that you see quantum technologies being appropriate for. So I don't want you to go too deeply because we'll have the chance to get underneath this. So just as we kind of walk down from the end here, where do you see the areas? And then I'll ask you why. But what are those areas to begin with?
So on the compute and algorithm side, there's certainly always an AI machine learning thing that we'll be able to do, a chemistry thing, and then an optimization thing. I think in the energy sector, optimization is very ripe on like unit commitment, grid optimization, grid operations. But we also are a quantum networking company, so we have grid security, grid protection, those types of opportunities. And we look forward to kind of exploring those spaces as we move forward. As a nuclear engineer, I'm also looking forward to maybe some like nuclear power operation optimizations or different explorations there.
I would agree with everything that Tim said, and if I could throw a couple of things on top of that, I'm very excited about solving optimal power flow problems, which is one of the most complex 2 to the n type problems where n is 100 million. So that's one that I'm excited about solving. Looking at energy for everyone, we're looking at in the last few years the cost of energy has risen significantly with electrification efforts, EVs, and now data centers coming online. So looking at how can we reduce the energy needs from especially AI training. So I think quantum plays a key role there. And finally, kind of my pie in the sky is fusion. So going off of Tim and his nuclear engineering background, I also worked in nuclear for a number of years. I think one of the most exciting forms of energy is fusion, and we will never get there without quantum.
All of the above, and I will add, in addition, maybe to kind of throw a quantum sensing flavor into the mix here, energy grid security and energy grid optimization, and the part that quantum sensing and timing can play in that arena.
So we make a lot of promises with quantum computing. It'll do this, that, and whatever. But seriously, guys, why can't we just do this with classical? So you mentioned to the end, bad exponential maybe is helped along by the good exponential, if you will, of quantum. But are you seeing really significant bottlenecks with classical computing, perhaps HPC, that is just making the need to get to quantum, as urgent as possible? So again, let's start from.
Yeah, I think that, if you look at the very long throw of things, we're seeing these AI workloads that do consume massive amounts of energy. And I think Paul and I both, are interested in just building systems that can just replace those workloads, even if they're like for like. Most of the very near term focus is like, how do we get to a quantum advantage so that we can kind of get these exponentials? But I think if you look in the very, very long term, if you can just do the same thing at lower energy, that's a benefit to humanity. And that's a very interesting thing that we should be able to do. But then we can also look at all of the quantum advantage things that are more near term.
Yeah, I think that's a really good point. And kind of continuing on the AI flavor, I would look at it as, okay, ChatGPT came out, ChatGPT 3.5 came out in November of 2022. So that was about 3 years ago. Since then, the models today are about 10 times that size and require about 10 times that amount of energy to train. We fast forward that into the future, that becomes a massive amount of energy, and then we all end up paying for that. So we know that utilities around the world are racing to build the amount of generation, battery storage, and other energy resources to be able to meet that. A few years ago, you had a 200 megawatt data center was like massive. And now people are talking about 5 gigawatt data center campuses. I mean, that is 5 large-scale nuclear power plants to power one data center. That is just incredible to think about that much energy going into one complex. So without the gains from quantum computing, it's going to be very difficult to get there. But then we run into Jevons paradox, where now we make it that much cheaper. Do we use that much more of it? So
That's right.
A wild time in energy.
Might not be a net gain. Right? And that's a lot of hallucination for 5 gigawatts.
It always, when I hear gigawatts, it always makes me think of Back to the Future for some reason. I'll add, I think one of the kind of the really interesting promises, and there's lots of interesting work happening in the industry in modeling some of these molecules that will have promises for things like new photovoltaics, new kinds of batteries, low temperature superconductors rather, and you just don't get there from here with traditional HPC. Even if you roll the clock forward 100 years, you don't get there from here. And so what a quantum computer at large scale, fault tolerance, will enable us to do is to actually do those calculations, do those computations, to design new molecules that will make energy generation and energy distribution more efficient. And that has enormous benefits, both in terms of cost of computation, in terms of cost of energy production, cost of energy distribution that will be felt all across the world.
And if I may add one data point, in Back to the Future, it was only 1.21 gigawatts, and we're already looking at 5.
Right.
And if I can add one more thing to what you said, Paul, I really like what you said of, we'll never get there with classical for some of these large-scale problems. And looking at some of the roadmaps that we've seen, some of the problems that we have in energy, we won't get there in the 5-year roadmaps of all the large-scale quantum computing companies. But that's fine, because we have plenty of other challenges that are intermediate, in terms of materials, optimization, fusion, and all these other things while we get to that optimal power flow problem that may be 10, 20 years out, even with quantum computing. So we have many problems for you, the quantum computing industry, to solve, and we would look forward to partnering with you, as we are doing with IonQ and with Infleqtion and other companies that are here, to solve some of those problems that can be tackled today that just are intractable with classical computers.
Now I do want to caution, though. one quantum computing company, not represented here, did a very nice poster of laying out their future big architecture. And for energy, they did put a little photo of a nuclear power plant, right? So truthfully, how much do we really know that quantum computers are going to be that much more energy efficient? Particularly, and here if you wish to speak more broadly about modalities, not just one in particular, we hear about cooling costs, right, and things like this. We hear about the advantages of room temperature, which means it's room temperature except where it's not room temperature, right? That tends to be true for almost everybody who talks about that. Is this real? I mean, do we have real data from the relatively small machines we have today and know about their energy uses? Or are we seeing a future where, in fact, it will ramp way up once we get to solving problems we care about? I threw this in, by the way. This wasn't in the prep. I just...
So there's, I forget who the physicist was who said this. It's attributed either to some famous physicist or to Yogi Berra, who said, prediction is very challenging, especially when it's about the future. Yeah. And so I think the best we do is extrapolate from what we know and the progress that we've made collectively as an industry. And I think it's quite stunning to be here. If you roll the clock back, say, when the first QWC happened 4 years ago, the amount of progress that has happened in the industry, if you look at what the likes of IonQ and Infleqtion and others have done and demonstrated on the roadmaps. And I think as far as the cooling costs are concerned and the costs of running these systems, there are some fundamental differences between modalities. So if you look at trapped ion and neutral atom, which are our respective modalities that are quite common in a way, these are systems that operate at room temperature. And even when you think about cooling in future generations of the system, this is cooling at 4 Kelvin, which is wildly different from dilution refrigeration. And so if you look at the kind of large-scale systems that some of the other modalities will require, yes, these are football field-sized systems that cost $1 billion to build and require a power plant to cool. It's a very different approach in the modality of, say, neutral atom and trapped ion, and even for the semiconductor-based approaches, which, whether you believe the kind of projections in terms of their ability to scale or not, regardless, will also operate at room temperature. So I think there are enough chips on the table, so to speak, between the modalities. And while, we no doubt have great faith in our companies and our modalities' ability to scale, there's a variety of modalities that are being pursued. There's a lot of chips on the table, and there's lots of pathways to large-scale fault-tolerant systems that don't require a nuclear power plant to power them.
Yeah. Oh, go ahead.
I mean, another way to add to that is that, it does depend on kind of the amount of the workloads that we can offset once we get to kind of these like points of quantum advantage. For example, we're working into CFD type workloads and we're only taking kind of a thin slice out of that workload today. But as we scale to larger components of that workload, that will kind of drive the unit economics of how much energy can we actually reduce in some of those types of paradigms. Similar to yours, our system is like just a 12K system, 12 kW. And we are running some experiments today on our system that's at Quantum Basel to actually grab the entire data that's coming off of our power distribution units that go into the systems to then do like an actual real data sample to know kind of like for a LLM fine-tuning model, what would the actual energy usage be, and then try to do the Yogi Berra thing to kind of predict forward from there. But we are looking forward to that. And then, it is incredible how far we've come as an industry because, even last year at QWC, we're just looking at how many qubits and what fidelities. And then this year at IonQ, we're starting to talk about unit economics. Like, what is the total bill of materials? Like, we can't spend $1 billion to build one quantum computer to solve one chemistry problem. These have to be reasonable, and they have to have reasonable energy usages.
Yeah, and I think ultimately it comes down to solving the right problem. So if you're looking at all the world of problems that are out there, not just energy, but everything, I mean, you have, with quantum, exponential speedups, polynomial speedups, and no speedup. So obviously you can filter out anything where you don't get a speed up because that just makes no sense to go after. But if you can focus on those polynomial and especially exponential speed ups, then it really helps you to justify the economics. And when you're talking about, 10, 15, even 100 kilowatts of power, I mean, from a grid perspective, that's a drop in the bucket. So when you're talking megawatts and gigawatts and tens or hundreds of gigawatts, that's when you really start raising some eyebrows. And what we're looking at from the AI side of things, which is kind of admittedly 90% of my job, people are talking about using over 100 gigawatts of electrical generation simply for training AI models by 2030. So, I mean, if you can reduce that by half or 90%, any of those numbers is huge. So there's massive value in finding the right use cases for quantum in energy.
Okay. And I know this was a little bit of a divergence from strictly speaking about quantum for energy, right? Turning around, but it is an interesting discussion. And there are studies around the world. In particular, there's one going on in France to try to do some extrapolations of what we know now of operating the systems we have. Because it's easy to say, oh, quantum is amazing, it'll use less energy. Well, prove it. What you know about 20 or 100 qubits isn't necessarily what you know about 10 million qubits. Right. Okay, so let's get back to the industry itself. All right. So I'm going to call out a few areas for comment, and you've mentioned some of them along the way. All right. So renewable energy forecasting, right? Well, gosh, today it's raining, it's cloudy, maybe solar is not so great, but not very windy today. Will quantum be useful, right, for this type of forecasting? And then that, of course, feeds into other elements of the grid utilization. So you don't have to comment on everything if you don't care to, just to be clear. But I thought we'd hit some of the topics that at least most people think about.
Yeah, I think the hard thing about the hard thing there is being able to deal with that kind of intermittent variability. So anytime you're trying to understand what a power demand and then power generation profile should look like for a forward-looking day, you have to kind of explore that very complex space of all of the variables that you mentioned, wind, solarity, all of these types of things. And so, quantum computers, in my mind, does kind of give us that like very large Hilbert space to kind of explore all those potential opportunities. And then the trick is always just in kind of how do you maybe kind of build a quantum sieve to then say, where are the outliers that we then need to plan for, right? But there's two ways to think about using quantum computers. There's the first way of that we're doing it today of how can we kind of plan for next day operations and then at least be ready. But then there's also kind of the day of like real-time decision making that then you have to implement in some kind of computational system. So I think that there's kind of like the unit commitment type things that we've both explored. But then there's also kind of the more advanced AI model training that doesn't have to go through some super complex set of business rules to decide, should I ramp up my coal or natural gas or nuclear to account for the reduced solar generation that I have? It's how do you have like quick models that can kind of make those decisions in an optimal way such that you're just operating efficiently.
And I think it comes down to what I said earlier about finding the right problem. So what are quantum computers best at? Modeling natural phenomena like weather. And really, when it comes to solar and wind, it's all about figuring out what is the weather going to do, which is a natural phenomenon. It's all based on physics. So it's a natural combination of quantum and energy application.
I would also insert here for just another precision agriculture, right? It's the same sort of thing, yes. Right? It's a big, being able to predict yield, maybe adjusting for it and so forth, with the same sort of information.
Well, the only thing I'll add, I fully agree with the comments earlier. I think there is a role that quantum sensing will have to play as well in giving us a better understanding of weather patterns, better ability to predict weather patterns, geologic patterns at a scale that's just not possible with existing classical sensors.
Mm-hmm. Okay, materials science, batteries. People talk about batteries. Now luckily, a lot of our batteries are lithium something or other, and lithium's that nice little atom that's sitting right there below hydrogen, right? So it's at least something we might imagine in the next few years, as opposed to a massive protein, let's say, or something like that. So how do you see quantum intersecting with material science? Maybe it's batteries, fuels, solar cells, things like this in general.
I think this is, of all of the potential use cases, and conferences like these, we talk about use cases in a broad array of industries. The one that to me feels nearest term will be absolutely modeling chemistry, right? I mean, this all goes all the way back to Feynman's original comments about you need a quantum computer to model nature. And I think the general consensus is we start to unlock that in a real way, in a commercially useful way, at around 100 logical qubits, kind of thereabouts. And the industry collectively is within striking distance of that. It's really, again, back to the predicting and the extrapolation. We all see a pathway to get there within the next year, next couple of years. We're going to have systems that are 100 logical qubits, the mega QOP, as it's referred to, a million logical quantum operations, and we can start to model these molecules in a way that simply is intractable with classical computing. In terms of novel battery chemistry, it's kind of outside my area of expertise, but my understanding is in kind of the low hundreds of logical qubits, we start to get really useful ability to design these new molecules that will enable us to have more efficient batteries, more efficient photovoltaics, and everything that comes along with that.
You see work coming out of the automotive industry as well. Volkswagen and BMW in particular are spending a lot of money researching that.
Yeah, and working with the solid metal lithium batteries from like QuantumScape, who incidentally uses the word quantum. It doesn't do anything in quantum computing. But those types of batteries that will have longer lifetimes, ability to charge faster, have better economics, will definitely feed into grid-scale battery storage, where the energy industry is already undergoing a massive transformation from, a few large-scale generation units with transmission and distribution, and then just consumers at the end, and just kind of a one-way flow of power. Now we're seeing prosumers, or producers and consumers combined, where an individual household may have a battery unit or a solar cell, and sometimes they're taking energy off the grid, sometimes they're putting it on. And then when you add in these batteries that can also be charged and discharged at will, it makes for a massively, I can't underestimate how much more complex that makes the energy system in terms of how you have to plan when you're the grid operator in a control room, not knowing exactly who has solar cells, because sometimes people install them without telling their utility, which is not allowed, by the way. Don't do that. It's a safety issue. But then you run into these issues where now you have two-way power flow on grids that were designed for one-way power flow, and you're charging and discharging at different times of the day. You have, in some cases, energy prices that go to zero or negative, meaning that the utility, your Duke Energies of the world or your Constellations, will actually have to pay money to put energy on the grid. Think about that business model. You have to pay money to sell your product. So we want to get away from that, because that doesn't make sense for anyone.
I've seen that happen, by the way, in other companies. I shall not tell you the stories, but I've seen that.
Yeah, but anyway, it ends up being that quantum computing can really help to alleviate, to optimize how and when you would charge these batteries, where you would place them for optimal performance, and what you're optimizing for. Are you optimizing for cost, reliability, or other factors?
And when you dive into kind of like grid operations, it's very easy to see kind of you have this like duck curve in terms of total like power demand that sits on the grid, and that there are large inefficiencies there that the power generators such as like Duke Energy and Constellation have to deal with. And to solve for those, you do need very large scale storage of energy, and that leads to these battery chemistry things. And so, we're very focused on that at IonQ. We do have some very recent research that we've done. There's this alphabet soup called AFQMC, Auxiliary Field Quantum Monte Carlo, that it took me a little while to memorize. But even in those
Is there going
types
to be a test on that?
There will be a test at the end. I hope everybody remembers. But we're able to show, even like on current scale NISQ machines, that we can start to explore some of these like chemical interactions at a very, very granular level in reasonable timescales. So our AFQMC algorithms are able to shorten some of these computations from months into weeks. And we're implementing these in very hybrid ways where we're using both QPUs and GPUs kind of in concert, implementing QPUs at like kind of the optimal path and or part of the overall workflow. And then we can kind of get to explorations of some of these new materials. But it takes scale of the quantum computers, as we know.
So in your responses, I'll just say you touched on several other things here. Grid management, optimization, energy storage, demand response, right? So this is all wrapped up. And even facility placement, right? Where do you put what, right? And then how you manage it. So for our last topic, we have just a few minutes left. So let me say, if we fast forward 50 years, and I'm frankly not going to be around at that point, but we look back, we're going to see, if you will, before fault tolerance and after fault tolerance. And in the grand scheme of things, post-fault tolerance will be a lot longer, right? And people may say, well, that was interesting to see what they were trying to do before we could have fault tolerance, right? And look at these amazing statements they made about this, that, and whatever. We certainly don't do that anymore, right? But what I want to ask you is, so realistically, yes, I know it's in the business models to try to do things before we have fault tolerance because you'd like to sell machines and whatever. But seeing that your companies are going to be around, in the case of the providers, right, for quite a while, post-fault tolerance, what do you think we're really going to need to wait for? So the problems we've talked about, you mentioned 100 logical qubits, and I agree. I think that's the threshold where things start to get interesting, right? Of all this wide range, kind of your concluding statements, what will we be able to do in the short term, and frankly, what will have to wait a little bit longer? So let's start with you. And
yeah, I think more near term are some of these kind of smaller scale optimizations, and then a lot of the like kind of near term value is, in my mind, kind of building out a vibrant ecosystem of like quantum developers, really. So there's like kind of a lot of community building, ecosystem building that we need to do to kind of get there, especially in the NISQ era. And we'll start to see small inklings of value kind of probably from some of the machine learning and optimization spaces. But then if I fast forward way out into like kind of the 50-year post-fault tolerance era, I think that's where you get to some really interesting areas where you're maybe kind of doing more like live AI training and inference all at the same time. I think there will be some interesting unlocks there where you're not having to wait for the next ChatGPT version, but you're able to kind of almost train live with access to quantum sensors and like very interesting data. But again, just one human's view of the very far out future.
okay.
Yeah, I think there will be all kinds of small scale problems that we solve in the interim. One of my favorite ones is recently being like 10 years ago, nuclear plants started introducing online noble metal chemistry into their water. And that significantly reduced the amount of CRUD, where CRUD is actually an acronym. It's Chalk River Unidentified Deposit, but CRUD on the fuel rods that was in the nuclear reactors. I think we'll have all kinds of new things. I mean, to me, that was a completely unexpected. Who would think putting noble metals into water would reduce corrosion of nuclear fuel? I think we'll have all kinds of material science problems that we're just like a step or two away from that quantum will really help us to solve. And then in the far future, we'll get into those grid scale optimization problems that are much, much more challenging.
Last word, Paul.
Maybe as I have the last word, I'll kind of get a little bit philosophical on you. I think we kind of, the world goes through these kind of phases of development, right? So if you go back to the Industrial Revolution, thermodynamics gave rise to the Industrial Revolution, right? And then you had electromechanics gave rise to the classical computing revolution. And we're just now coming into the quantum mechanics phase where humanity is using quantum mechanics to do useful things. And I just think 50 years, we just don't know. If you went back to the beginning of the electromechanics revolution and said, would we have ChatGPT 50 years from now? It was unimaginable when the ENIAC was first developed. And I think in the same way, we can make prognostications of what we think the world looks like in 50 years. I think if I'm alive in 50 years, I'll be very, very old. But if I'm alive in 50 years' time, I don't think we can possibly imagine what this revolution is going to create. And we're just at kind of the first rung of the ladder.
So thank you. We've talked about several things with energy, but I think we've also, your discussions, were good at generalizing a little bit more about the types of problems. And so energy will be a fascinating place to watch as we proceed. So join me in thanking the panelists.